In this video, we will identify and graph conics given an equation. But first, we need to recall some facts about polar equations of conics. The following polar equations represent conics with one focus at the origin and eccentricity e. Assume that the positive x-axis represents the polar axis. For r equals e times p over the quantity 1 plus e times cosine of theta, the directrix is perpendicular to the polar axis and p units to the right of the pole. For r equals e times p over the quantity 1 minus e times cosine of theta, the directrix is perpendicular to the polar axis and p units to the left of the pole. For r equals e times p over the quantity 1 plus e times sine of theta, the directrix is parallel to the polar axis and p units above the pole. For r equals e times p over the quantity 1 minus e times sine of theta, the directrix is parallel to the polar axis and p units below the pole. If the eccentricity is equal to 1, the conic is a parabola, and the axis of symmetry is perpendicular to the directrix. If the eccentricity is less than 1, the conic is an ellipse, and the major axis is perpendicular to the directrix. If the eccentricity is greater than 1, the conic is a hyperbola, and the transverse axis is perpendicular to the directrix. Let's try some examples. Identify the conic from the equation r equals 3 divided by the quantity 2 plus 2 times sine of theta. To do this, we will rewrite the equation in the general form most closely resembling this equation, which we saw previously as r equals e times p over the quantity 1 plus e times sine of theta. Take the right side of r equals 3 over the quantity 2 plus 2 times sine of theta and divide each term in the numerator and denominator by 2. Thus, we get 3 halves over the quantity 1 plus sine of theta. Comparing this equation to its general form, we see that e is 1 because the coefficient of sine simplifies to 1. Since e equals 1, our conic is a parabola. Now let's graph this parabola. Graph the conic from the equation r equals 3 over the quantity 2 plus 2 times sine of theta. Because we found that this conic's eccentricity is 1, we know that the graph should show a parabola. Let's create a table of values to help us graph this equation. We will use theta values of 0, pi over 2, pi, 3 pi over 2, and 2 pi. So, starting with 0, we substitute 0 for theta in our equation r and evaluate. Thus, r in this case is 3 halves. An ordered pair in the context of polar coordinates is of the form r theta, so the point we generated is 3 halves 0. Be careful that you do not mix the order. Next, we can substitute pi over 2 for theta in our equation r and evaluate. This time, r equals 3/4, so our polar coordinate is 3/4 pi over 2. When theta equals pi, we get r equals 3 halves, so our polar coordinate is 3 halves pi. When theta equals 3 pi over 2, the denominator of the equation for r simplifies to 0, so r is undefined when theta is 3 pi over 2. Finally, when theta equals 2 pi, we get r equals 3 halves, so our last polar coordinate is 3 halves 2 pi. Using the points we generated, we can graph this equation on a polar coordinate plane as shown. The graph looks like a parabola, which confirms our previous assessment.